Hello everyone, this is Onnera Afroj and my ID long is 120130111. I am the student of Begumruka University, Rangpur and the Department of Chemistry. Here presents our honorable course teacher, MD Mustafa Karim Sharafat sir, and all of my friends. At first, take my salam. Assalamu alaikum. Today, my selected topic is Van der Waals equations, its applications and limitations. Then at first I can explain the history of Van der Waals equations. In 1873, J.D. Van der Waals modified the ideal gases for real gas by including the effect of gas molecule interaction. Then the interaction will be two molecules, and this properly is known as Van der Waals equations. Then the next slide, table to content. So content 1 is represent that the Van der Waals equations derivations, corrected volume, corrected pressure, and the Van der Waals equation derivations. Then the two content is unit of A and B in Van der Waals equations. Then the three content, limitations of Van der Waals equations. Then the last content, summary of Van der Waals equations. Let's see the next content, corrected volume in Van der Waals equations. When a gas is compressed, molecules are pushed as closer. That repulse forces operates between them. Further increases the pressure is observed by the molecule themselves because molecules have definite volume. So volume available to gas molecule V equal to V vessel minus V molecule, and V is free volume V molecule equal to NB, where N equal to number of molecule of number of molecule and B is individual volume 1 mole of gas. Here V equal to V vessel minus NB, and that is the number 1 equation. Then the next slide represents the pressure correction in Van der Waals equations. Each molecule in the middle of gas is attracted by all sides, so the attraction forces are cancelled out. When a molecule is attracted both other in the wall of container, it expresses a force of attraction towards other molecules. Pressure being observed on the walls of vessel is less than ideal pressure. So P observed equal to Pi minus P dash. Here Pi equal to ideal pressure and P dash equal to pressure lessened due to molecule attracted. Pi equal to P observed minus P dash. That is the equation number 2. Then the next slide represents the pressure correction also, and suppose molecule A are strike wall of the container and molecule B are pulling them inward. Then the equation stand by P dash proportional to Ca into Cb. Here Ca and Cb represent that the A and B molecule. Let N equal to number of molecule of A and B and V total volume. Then the equation stand by P dash proportional to N by V and into N by V. Here N by V we get Ca into Cb. P dash proportional to N square by V square, and the last P dash equal to A N square by V square, where A is called coefficient of attraction per volume and it has a constant value, and put value in equation 2. Then the next slide represents the Van der Waals equations. We know ideal gas PV equal to nRT. So put values from equation 1 and 3 in the ideal gas P plus A V square by N square V minus NB equal to nRT. For 1 mole of gas, we know that P plus A by V square V minus B equal to RT. Then the next content, we can see the slide, unit of A and B in Van der Waals equations. Unit of A we can see from Van der Waals equation P plus A N square by V square. Here A equal to P V square by N square, and the A unit of atmosphere decimeter to the power 6 and per mole square. Unit of B decimeter cube and per mole. Decimeter cube per mole. Then the next slide represents the limitations of Van der Waals equations. Van der Waals equations fail to high temperature and low pressure. Then the last slide represents the summary of Van der Waals equations. Real gases interact with each other and take up volume in the container. We get from the ideal gases P equal to nRT by V minus NV minus AN square by V square. If the gas is under ideal gas conditions, the Van der Waals equations reduces to the ideal gas law. We know PV equal to nRT. Then that is the end of Van der Waals equations, its applications and limitations. Thank you.